Hello, my dear students, with you Mr. Mahmoud Shirbini, your chemistry teacher, and today we will complete Unit 5 and explain Lesson 2 Strong Nuclear Forces. We know all that the nucleus consists of protons and neutrons. While protons have positive charge and neutrons have neutral charge. Okay, so there is two forces inside the nucleus, okay, between protons and each others, and this called repulsion force. This repulsion force between protons and each other. Why? Because the protons have same charge. Okay, so this force is called repulsion force, or has another name as Coulomb electric force. Okay, there is another force that bind the components of nucleus with each other. This force is called strong nuclear force. Okay, this force bind the components of the nucleus with each other. Okay, there is attraction force between three things inside the nucleus. Okay, number one, between the protons and each other. Number two, between neutron and neutrons. Number three, between proton and neutron. Okay, so we have three attraction force inside the nucleus between proton and proton, neutron and neutron, proton and neutron, and one repulsion force between proton and proton. Okay, the stability of the nucleus, or the nucleus keeps its stability as the strong nuclear force is larger than the repulsion force. Okay, so the atom become stable. Okay, we have many properties for nuclear or strong nuclear force. Okay, number one, that this force has a great power. Okay, number two, that this force exists between proton and proton, neutron and neutron, proton and neutron. Okay, number three, that this force works only when spaces between nucleons are very small. Okay, so now we have three properties for strong nuclear forces. Number one, they have a great power. Number two, there is attraction force between proton and proton, neutron and neutron, proton and neutron. Number three, that this force works only when spaces between nucleons are very small. Okay, now we will talk about the nuclear binding energy and calculate it. The nuclear binding energy, that the energy that bind the components of atoms or the components of the nucleus with each other. Okay, we know all that any element X has two numbers: the atomic number, which represented by Z, and the mass number, which represented by A. This number represents the number of protons, while the mass number represents the sum of protons plus neutrons. Okay, the proton have a fixed number or a constant value for its mass equal 1.00728 atomic mass unit, and the mass of neutron equal 1.00866 atomic mass unit. Okay, so the mass of proton and the mass of neutron is a constant value. Okay, if we have an example for helium, He 2 4. So the number of protons here equal 2 and the number of neutrons equal 2. Okay, so if we can calculate the theoretical mass, or this called the atomic mass. If we can measure the theoretical mass for helium atom, we have 2 protons and 2 neutrons, and each proton, its mass is 1.007 and the mass of neutron 1.008. So the mass, or the atomic mass for helium, this mass is called theoretical mass, okay, which equal the number of protons times its mass plus the number of neutrons times its mass. Okay, so the sum of mass, or the two masses, equal the theoretical mass, which equal 4.03, and this mass is called theoretical mass. This mass is called theoretical mass, but the practical mass for the helium equal 4. Okay, so there is a difference between the theoretical mass and practical mass. This difference, or this mass defect, the nucleus used it to make the binding energy, or to make the binding between the components of nucleus with each other. Okay, so the difference between the theoretical mass and practical mass, the nucleus used it to make the binding between the components of the atom. So the mass defect equal theoretical mass minus practical mass. Okay, the practical mass for each element has a constant value. Okay, theoretical mass, we can calculate it from the number of protons times its mass plus the number of neutrons times its mass. Okay, we have a relation to calculate the nuclear binding energy, or the energy to bind the component of the nucleus together. Okay, the relation used to calculate the nuclear binding energy is E equal mass times 931, while energy here is the nuclear binding energy. By million electron volt. Million electron volt is a unit of nuclear binding energy. The mass defect by unit atomic mass unit. The mass defect equal the theoretical mass minus the practical mass. Okay, while theoretical mass equal number of protons times its mass plus number of neutrons times the mass of one neutron. Okay, so this relation is used to calculate the nuclear binding energy for all nucleons for the atom. Okay, for example, helium He24, if we use this relation to calculate the nuclear binding energy for all the 4 nucleons. Okay, to calculate the nuclear binding energy for one nucleon, so the relation will be nuclear or binding energy per nucleon equal the total binding energy divide the atomic mass, okay, which is represented here by number 4. Okay, we have an example for helium atom to calculate the nuclear binding energy per nucleon. Calculate the nuclear binding energy per nucleon in the nucleus of helium atom He24, knowing that its actual mass 4.003150, atomic mass unit, the mass of proton equal 1.007 and the mass of neutron equal 1.008. To calculate the nuclear binding energy per nucleon, we must know, or we must have the nuclear binding energy or total binding energy divide the atomic mass. Okay. To calculate the nuclear binding energy, the total binding energy equal mass defect times 931. Okay, the first step to calculate the mass defect, and to calculate the mass defect equal theoretical mass minus actual mass. Okay, so we need to calculate in the first step the theoretical mass. Theoretical mass equal the number of protons times its mass and number of neutrons times its mass. The number of protons here equal 2 and the number of neutrons equal 2. So the theoretical mass equal number of protons 2 times 1.00728 plus 2 number of neutrons times the mass of 1 neutron. Okay, the theoretical mass equal 4.0318 atomic mass unit. Okay, the next step to calculate the mass defect. The mass defect equal theoretical mass minus actual mass. The actual mass equal 4.003150. Okay, so mass defect equal theoretical mass minus actual or practical mass. 4.0318 minus the practical mass 4.00150. Okay, so the mass defect equal 0.03038 atomic mass unit. Okay, now we can calculate the nuclear binding energy by mass defect times 931. The mass defect equal 0.03038 times 931. Okay, it will be equal 28.28 million electron volt. Okay, so we need here to calculate the nuclear binding energy per nucleon. The nuclear binding energy per nucleon equal the binding energy or the total binding energy divide the atomic mass. Okay, the atomic mass equal 4, so the nuclear binding energy per one nucleon, nuclear binding energy per nucleon equal the total binding energy divide the atomic mass. Okay, 4. It will be equal 7.07 million electron volt. Okay, by increasing the number of, or by increasing the value of nuclear binding energy per nucleon, the stability of the element increase. Okay, the nuclear stability of the element increase. So by increasing the nuclear binding energy per nucleon, the stability or the nuclear stability increases for the element. Okay, we have another example for example to calculate the nuclear binding energy in joule of atoms in nucleus, knowing that the value of A equals 6, Z equal 3, actual mass equal 6.015, the mass of proton equal 1.007, the mass of neutron equal 1.008. Okay, the idea of this problem to calculate the energy in million electron volt, then convert it to joule. Okay, so the nuclear binding energy equal mass defect times 931. Okay, to calculate the mass defect we need to calculate first the theoretical mass, and theoretical mass equal number of protons times the mass of one proton plus number of neutrons times the mass of one neutron. Okay, the number of proton here is 3. Okay, as Z represent the atomic number, which equal the number of protons and the number of electrons. So the theoretical mass equal 3 times 1.00728 plus number of neutrons here equal A minus Z. Okay, which equal 3. So 3 times 1.008 66. Okay, so the result equal the theoretical mass, which equal 6.0478 atomic mass unit. Okay, the second step to calculate the mass defect. Mass defect equal theoretical mass minus actual mass. Theoretical mass here equal 6.0478 minus practical mass 6.015, so it will equal 0.03282 atomic mass unit. Okay, the next step to calculate the binding energy in a unit million electron volt. So the energy in million electron volt equal mass defect times 931, but the result here by million electron volt. Okay, which equal 30.55. Okay, to calculate the nuclear binding energy per or in joule, we can convert the energy by million electron volt to energy by joule. Okay, to convert the energy from million electron volt to joule, we will multiply the result here times 1.6 times 10 power negative 13, and this is a constant number. Okay, in the last lesson, so it will be equal 4.9 times 10 power negative 12 joule. Okay, we have another solution for this problem to convert the mass from atomic mass unit to kilogram and use the relation E by joule equal mass by kilogram times C square. Okay, this another solution for this problem. Now we have finished explaining the first part in lesson 2 in unit 5. In the second part we will talk about the nuclear stability and the concept of quarks. Okay, thanks.